Alright, hello everyone. So it's been quite a while since I uploaded my last YouTube video. I just, it was exam season. I had my school exams going on, and right now I have winter break, so I thought it's a good idea to, you know, make a video. So, um, today I'm doing 9701 May June 2015, paper 11 of chemistry, AS level. Okay, so let's start. Question number one. The diagram shows a Boltzmann distribution of molecular energies for a gaseous mixture. The distribution has a peak labeled P on the diagram. Okay, so this is your peak. What happens when an effective catalyst is added to the mixture? Okay, so they're saying, well, I mean, if you add a catalyst, what will a catalyst do? We all know that a catalyst, it lowers the activation energy, right? So it lowers the activation energy, which means this, the line they've shown for your activation energy, now your new line is somewhere over here, for example. So this is your new activation energy, okay? So that's all that the catalyst does. It doesn't really shift the peak or anything like that. So if they're saying the height of the peak decreases, we can immediately cross out that option, right? But then the height of the peak remains the same. That's the truth. And then the activation energy moves to the right. Well, actually, this is your left, right? So what's happened? Your left, right? That sounds funny, but anyways, you're moving to the left. Okay, so your activation energy has actually moved to the left, right? Right. I want to say right, but I mean I want to say left, comma right, like like that, but that doesn't sound right. So that's the problem. But yeah, so it moves. The activation energy moves to the left. So that means your answer is D. So it's moved to the left and your peak has remained the same. Your whole graph has remained the same. The only thing that has happened is that your activation energy has shifted to the left, right? Okay. So which quantity gives the best indication of the relative strengths of the hydrogen bonds between the molecules in liquid hydrogen halides? Okay, so you have HCl, HF, HBr, sorry, actually I should say HF, HCl, uh, fluoride, chloride, and then bromide, and then iodide and acetate. Okay, so Hi and then Hat. Okay, so the relative strengths of the hydrogen bonds between the molecules in liquid hydrogen halides. So hydrogen bonds are actually intermolecular forces, right? So they're intermolecular forces, which means that like this bond that we're talking about here, this is a covalent bond, right? But we're just talking about intermolecular forces, meaning that if we have one molecule of HCl and then it's hydrogen bonded to another molecule of HCl, okay? So there are hydrogen bonds between it and another molecule of HCl. So partially positive and partially negative, and then partially positive, partially negative. So it's hydrogen bond. Actually, that's not the correct way to draw it, is it? Yeah, it should be H2Cl, right? Yeah, and then from a lone pair of Cl actually. Yeah, see, I should really revise my AS chemistry, but yeah, that's how you do it. And it's better if you draw it in a line, I think. Yeah, so you can do that. You can draw it in a line. A better way of doing it, I suppose. And you have a lone pair on fluorine, and then it's bonded like that. So you're basically talking about intermolecular forces, okay? Which means that if you're talking about bond dissociation energy, that means the dissociation of the covalent bond, right? But that you're not supposed to be talking about covalent bonds, you're just talking about the intermolecular forces. So that cannot be the correct answer. If we're talking about enthalpy changes of formation, then that's like, for example, H2 plus Cl2 gives you 2HCl, right? Or actually, if it's for 1 mole of the substance, then because that's what enthalpy change of formation are, right? Like 1 mole of the substance is formed. So basically you're breaking the HH bond, you're breaking the Cl-Cl bond, and then you're forming an HCl bond. So again, you're just dealing with covalent bonds, but you're not supposed to be dealing with covalent bonds if you're talking about hydrogen bonds, because that's just intermolecular forces. And enthalpy changes of solution, again, like if you are like you have enthalpy change of solution, actually that's an interesting thing that they've asked, because enthalpy change of solution actually refer usually to ionic compounds, right? Like ionic solids and stuff like that. But HCl, HF, HBr, HI, these are all covalent compounds. So I don't understand why that would even be an option. Like, why would you even talk about their enthalpy changes of solution, right? So that's wrong. And then you have enthalpy changes of vaporization. That actually it probably is your answer. Why? Because what is vaporization? Vaporization is your change of state from liquid to gas, right? So what's happening is that, like for example, if you have H2O, your H2O liquid is just changing to H2O gas, but then you still have this molecule, like H is still bonded, like there are two hydrogen atoms still bonded to an O atom. That's the same, but it's just that the state has changed from liquid to gas, right? And that means your intermolecular forces have become weaker. And that means because in the, like, if you're talking about hydrogen bonds, then the hydrogen bonds are intermolecular forces, right? Like in HF, HCl. So HCl, HF, you have hydrogen bonding, right? So in those two at least, or so you have hydrogen bonding, which means that your hydrogen bonding is going to be weaker when your substance gets vaporized, right? Or when HF gets vaporized, when HCl get vaporized, then your hydrogen bonds become weaker. Okay, so that means that if you're trying to get the best indication of the relative strengths of the hydrogen bonds, then your best option would be the enthalpy changes of vaporization over here, right? Because all the other first two are talking about covalent bonds, and then the third one is talking about ionic compounds, and then fourth one is talking about intermolecular forces, actually. So that is your best bet, basically. Yeah, next question. So what are they saying? Use of the data booklet is relevant to this question. Okay. What I can do is maybe even I can open up my data booklet over here. So let me try to find it on my desktop. All right. So maybe that would help. Okay. So actually no. Or maybe yes. Just do that. Okay. This is my data booklet, and now I'll look at the question. Okay. Right, technical difficulties, let's just say. So anyways, use of the data booklet is relevant to this question. 1 gram of carbon is combusted in a limited supply of pure oxygen. 0.50 grams of the carbon combust to form CO2, and 0.50 grams of the carbon combust to form CO. So what's happening is you have carbon plus oxygen giving you firstly CO2, and then another equation is C plus O2 gives you CO, right? So this one is not balanced, so what you do is you'll just make this 1 by 2, right? And now they're saying that the resultant mixture of CO2 and CO, so this is 0.50 grams of carbon here, and this is 0.50 grams of carbon here, right? In total, you have 1.00, and they said 0.50 becomes CO2 and 0.50 becomes CO. So the resultant mixture of CO2 and CO is passed through excess of NaOH, and the remaining gas has been collected and dried and collected. So the thing is that NaOH, we know that it's a base, right? And CO2, it's an acidic gas, so it will react with NaOH. Okay, CO2 will react with NaOH, but then CO, that's a neutral gas. Since it's a neutral gas, that means that after its reaction with NaOH, we won't have any more CO2. Like the reaction will take place between CO2 and NaOH, right? So we'll get, like, I suppose we'll get uh, what can we say? We'll get Na2CO3 plus H2, or we can say NaHCO3 perhaps even plus H2, or something, something like that basically. And so that will happen, but then we still have the CO neutral, and they're asking you to find the volume of the remaining gas. Now the remaining gas is just CO, so basically we just have to find the volume of CO. Okay, so if we have 0.50 grams of carbon, how many moles of carbon do we have? N equals to m over mr, so mass over the molar mass. So 0.50 over, if you check the periodic table, it should be 12. I think, yeah, I'll use this periodic table. Okay, so that is just 12. Where am I even looking? This is 12. And I'm just going to write that, 12.0. So 0.50 over 12 is basically 0.0416 moles. Okay, and now if I look at the molar ratio, it's 1 carbon is to 1 mole of 1 molecule of carbon monoxide, right? So the molar ratio is 1:1 basically. So if this is 0.0416, then that means we also have 0.0416 moles of CO, right? And now what I can do is I can find the volume using the formula n equals to V over 24, right? Because they said it's at 25 degrees Celsius and 1 atmosphere pressure, which basically means room temperature and pressure. So I can use this equation, n equals V over 24. So V equals to 24 n then. So V equals to 24 multiplied by 0.0416 recurring. You can just use your calculator value, and what do you get? Answer multiplied by 24. So I get 1 decimeter cube. That's what I got on my calculator, and that means that the answer is basically A. Okay, so next question now. In oxygen difluoride OF2, fluorine has an oxidation number of -1. So usually, if we have H2O or we have CO2 or any compound, usually our oxygen has, because it's the more electronegative element, right? It's the second most electronegative element actually. FONClBr. That those are the five most electronegative elements. So then oxygen is second. Oxygen is usually the most electronegative element, which means that it takes preference and you give it the negative oxidation number basically. So over here it has -2, over there it has -2, right? But then in OF2, because actually fluorine is the most electronegative element in the periodic table, so fluorine takes preference. You will give fluorine the negative oxidation number. So that's why over here fluorine has an oxidation number of -1, and you have to find the oxidation number of oxygen because it's less electronegative than fluorine. Okay, so if this is -1, then -2 times -1, because there are two fluorine atoms, plus x I'm taking as the oxidation state of oxygen, equals to 0. So then x is equals to +2. So that means over here oxygen has a oxidation number of +2. Well, that's funny. Oxygen has an oxidation number, but yeah, it does. So the answer is basically +2 over there. Now, what is oxidized and what is reduced in this reaction, right? So oxidation is the loss of electrons and reduction is the gain of electrons, right? So basically, if fluorine is -1 over here is just a pure element, right? So its oxidation number is 0. So -1 to 0, that is an increase in oxidation number, which means that it is becoming oxidized, right? It's losing electrons. So that means that fluorine over here is oxidized. So my answer is either going to be A or B. Now, if you look at oxygen, over here it's +2, as I showed you, and then over here it's -2, and over here it's -2. Okay, so oxygen in OF2, they said, so it's going from +2 to -2, right? So +2 to -2 means it's decreasing in oxidation number, which means it's being reduced, right? So this is reduction, and that means it's gaining electrons. So oxygen in OF2 is actually reduced. And then sulfur, I'll just use a different color. So sulfur over here, if oxygen is if oxygen is -2, right, in SO2, if oxygen is -2, then there are two oxygen atoms, that's 2 times -2, and then plus x, I'm taking sulfur as x, equals to 0, because your overall charge of the compound should be 0. So then x is equals to +4. So that means sulfur over here has an oxidation number of +4. Over here in SO3, what's the oxidation number of sulfur? Well, you have three oxygen atoms, so you'll do 3 times -2 plus x equals to 0, because the overall charge of the compound should be 0. X is equals to +6. Okay, so it's +6 over there, and so it's going from +4 to +6. That means that it's increasing in oxidation number, and if it's increasing in oxidation number, that is oxidation, right? So it's becoming oxidized, and so that means sulfur is oxidized, which means, like, where do I have three ticks? I have three ticks here, so that means my answer is B. Okay, so let's go to the next question now. Oh yes, ideal gas questions, my favorite. So use of the data booklet is relevant to this question. The gas laws can be summarized in the ideal gas equation below. So 0.96 grams, that's the mass is of oxygen gas, is given contained in a glass vessel of volume 7 into 10 power of -3 cubic meters at a temperature of 30 degrees Celsius. Assume the gas behaves as an ideal gas. What is the pressure in the vessel? Okay, so PV equals to nRT, because N equals to M over MR, right? So I can rewrite that as PV equals to M over MR into RT. Okay, then what I can do is I can just shift the volume to the other side. Like if it's in the numerator here, it becomes in the denominator there. So then I get P equals to MRT over the molar mass MR into the volume. Okay, so now I just substitute my values into this equation that I have. So P equals to mass, which is 0.96, multiplied by the ideal gas constant, which you can find in your periodic table. See, it's upside down for me, but So you have it over there. It's 8, sorry, not in periodic table, I mean to say your data booklet or whatever. So it's 8.31 joules per Kelvin per mole. If you write down the units, you will actually see that they, in your process, if you they cancel out, and then you get the pressure units, just pascals, That's a nice thing. Anyways, so 8.31 joules per Kelvin per mole. So 8.31. Actually, they don't cancel out that well. Anyways, they would, basically, because, I guess newtons per square meter and blah blah blah. But basically, you would get the pressure units because pascals are equal to newtons per square meter, and then Newton equals to. That's actually more physics than chemistry, but maybe I'll do a physics passive session as well. That's the topic called, I guess, homogeneity and stuff in physics. Pretty cool topic. Anyways, temperature is, they give you temperature in Celsius, so you should convert it to kelvins because this is your thermodynamic temperature. Thermodynamic temperature is represented by the letter T. If you had theta, that would mean your temperature in degrees Celsius. But thermodynamic temperature is the temperature in Kelvin, and it's represented by a capital T usually. So that is 30 plus 273 because that's the conversion from Celsius to Kelvin, right? You add 273. Okay. So then your MR of oxygen gas means this O2, which means your molecular mass is going to be 16.0 multiplied by 2, right? Because you have two oxygen atoms, so that's going to be 32.0 grams per mole. So that's the unit of MR and AR and all that. So it's 32.0, okay? And now what I'm going to do is I will multiply it by the volume, which is in the ideal gas equation, your volume should be in cubic meters, and it is in cubic meters here. So we're lucky to have that already. Like we don't have to do any further conversions. And now we just put that in our calculator and find the answer. So 30 plus 273, and then answer over 32 times 7 times 10 to the power of minus 3. So I get in my, okay, and they're actually, so this answer that I get is actually going to be in pascals, but they're like all the options are in kilopascals. So to convert from pascals to kilopascals, I'm just going to divide by 1000. Okay, so whatever answer I get in my calculator, I'm going to divide it by 1000. So if you want, I can just write it over here, divide by 1000. Okay, so then what do I get? I get 10.791 kilopascals. Okay, so if I get that, then what option is that? That is option C, right? Because this is approximately 10.8 kilopascals, which is option C. So that's the answer. Next question. 1 mole of phosphorus 5 chloride PCl5 is heated to 600 kelvins in a sealed flask of volume 1 cubic decimeter. Equilibrium is established and measurements are taken. The experiment is repeated with 1 mole of phosphorus 5 chloride heated to 600 kelvin, so the same temperature, but in a sealed flask of volume 2 cubic decimeter. So your volume is changing. Okay, that's an important thing in this question. The volume is changing, and the change in volume does obviously change the concentration, because what is concentration? Concentration is your moles over the volume, right? So if concentration is moles over volume, that means if your volume is increasing, your concentrations would decrease. So I'll just write it down. For example, if we initially we had PCl5 as X, okay, and then this was 0 and this is 0, right? Now this dissociates basically into PCl3 and CCl2, right? Because the forward reaction takes place to establish equilibrium and stuff, right? So then this becomes like X minus Y, okay? And this becomes Y, and this becomes Y. So you X minus Y over here, and this becomes plus Y, and this becomes plus Y, right? Because there's a 1:1:1 molar ratio. So that's why I got these values. And these are my molar ratio, like these are the moles, the number of moles, right? But if I were to look at the concentrations, then in experiment number 1, my concentration, like if I use this equation, I'm just going to line it up over here, okay? So I hope that doesn't make everything messy, but yeah. So firstly, like if I have my equilibrium, these are my equilibrium moles, right? Equilibrium moles. So now if I have my equilibrium concentrations for the first one, experiment 1, I'm going to have X minus Y over 1. And this is going to be Y over 1, and this is going to be Y over 1 again. But if I have experiment 2, then for experiment 2, I have X minus Y over 2, and this is Y over 2, and this is Y over 2. Now obviously, like X minus Y is greater than half of, like, because this is basically half of X minus Y, right? So half of X minus Y, obviously X minus Y is greater than half of X minus Y, and Y is greater than half Y, right? Like this is half Y. So that means that your equilibrium concentrations are smaller in experiment 2, right? And in experiment 1, you have bigger equilibrium concentrations, right? As you can see. Okay. So the equilibrium concentrations of PCl3 and PCl2 are higher in the second experiment. That's wrong. The equilibrium concentration of PCl5 is lower in the second experiment. That's right, because this is lower, right? All of these three are lower in the second experiment because you have a greater volume. That means you will immediately have a lower concentration, right? So the equilibrium concentration of PCl5 is lower in the second experiment. That's right. The equilibrium concentration of all three gases are the same in both experiments. No. The equilibrium moles are the same in both experiments because you have x minus y, y, and y. But the concentrations, you have to consider the volumes as well, right? So the volumes are not the same. Sorry, that means the concentrations are not the same, right? So the value of the equilibrium constant is higher in the second experiment. That's also wrong because actually the only thing that can change equilibrium constants like Kc and Kp, and there are others as well that you learn in A2. So Ksp and Kpc and many others. So those are all only changed or affected by temperature. So only temperature can change equilibrium constants in most cases. So basically, basically if my concentration is decreasing here, my concentration immediately increases in these two, right? So that means your mole fraction, like I mean to say your molar, no, what should I say? Like my Kc expression is what? It's PCl3 multiplied by Cl2 multiplied by PCl5, right? That's my Kc expression. And now if PCl5 is decreasing, that would mean my Kc would increase, right? But simultaneously, my these two, sorry, actually I'm missing the opposite thing. So if these are increasing, right? So then that again is, wait, I am saying something wrong here. Yes, actually that's, I am wrong. So for example, if like for example, if your concentration of PCl5 decreases, then these two will, like I'm just saying, but actually that's not what is happening in this question. But the only thing that can change Kc is temperature. But for example, if PCl5 was increasing in concentration, equilibrium would try to oppose that change by shifting the equilibrium to the right hand side. So then these two would increase. So if this is increasing and these are also increasing, well, if this increases, Kc decreases. If the numerator things increase, then the Kc increases. So that means overall there's no change. And similarly, if your PCl5 was decreasing, then equilibrium would try to oppose that change by shifting equilibrium to left hand side. That means that these would decrease as well. So if this is decreasing and your denominator things are also decreasing, then your Kc has remained unchanged. That was a really long-winded explanation, but basically my point is that Kc is not changing, okay? Or Kp or anything. So that means your answer is basically B, as I showed you over here. Next question. The standard enthalpy changes of combustion of glucose and ethanol are given as -2820 and -1368 kilojoules per mole respectively. Glucose C6H12O6 can be converted into ethanol. What is the standard enthalpy change for this reaction? Okay, so what I'll do is I'll just make arrows and stuff. So CO2 plus H2O, and I'll make downward pointing arrows from the products as well as the reactants. Okay, so products, if you combust C6H12O6, so I should perhaps also include oxygen on both sides, but it doesn't really, I mean, it does matter in like terms of the making a proper Hess cycle, but in terms of your calculation, it doesn't really matter if you add oxygen or not, because if you add oxygen, you will need to balance the equation as well. So just do that. Make sure you have a balanced equation. So I have 6 oxygen over here, so I would just make this 3O2, and on this side I have 2 plus 4, that's also 6 oxygen, so this is 3O2. So again, it doesn't really make a difference because you have the same number of moles of oxygen on both sides, so they cancel out sort of, and you don't really need to include them, but if you want, you can. It's a good practice, I suppose, in terms of good bookkeeping and stuff. So anyways, combustion of glucose is -2820. That means I will write this as -2820. It's just 1 mole of glucose, right? And then combustion of ethanol is -1368. So -1368, but then we have 2 moles of ethanol, right, in the balanced equation. So I will make this and multiply this by 2. Now carbon dioxide, if you combust it, it's carbon dioxide, right? What would you get further than that? So I won't really include that because carbon dioxide going to carbon dioxide is not really a change, right? Carbon dioxide gas going to carbon dioxide gas especially. So there's not really a change. So now what I'll do is I'm finding the standard enthalpy change of this reaction. So I'll just follow the arrows. Like this is one route, right? But the other route is this one. So I'll just follow the arrows. If I follow this arrow, I get -2820. and then so delta H equals to minus 2820. And then if you follow this arrow, you're going against the arrow, right? So you'll make this minus into a plus 1368 times 2. Okay, so that's the calculation I have to do, and let me do that calculation. So I get minus 84 kilojoules per mole. Okay, that is the answer I get, and that is option B. So that's my answer. And yeah, that's awesome. Next question. In which reaction is the underlined substance acting as a base? So what is a base? A base is basically a proton or H plus accepted, right? According to the Bronsted-Lowry acid-base theory. But then actually there's a more inclusive definition which you don't really study at A levels, I think, which is called the Lewis acid-base theory. So that basically makes the definition broader, because you have to realize that not every reaction actually has H plus, right? Like in some reactions you don't even have hydrogen atoms at all, or hydrogen ions or anything. So then a more inclusive definition is in terms of electron pairs. So that's what the Lewis acid base theory defines acids and bases as. So that in that definition, a base is basically a lone pair donor, and an acid is a lone pair acceptor. So I just that's what I keep in mind always, that if I'm thinking about a base, I'm either trying to find a proton H plus acceptor or a lone pair donor. Okay, and if I'm thinking of an acid, it's a H plus donor or a lone pair acceptor. Okay. So in which reaction is the underlying substance acting as a base? So over here, H2SO4, well, we already know that H2SO4 is sulfuric acid, right? So there's low chance of it being a base, but even if we see it, it's donating an H, right? It's donating one of its H plus to become H2SO4 minus, and then HNO3 is actually accepting a lone pair. So actually, H2SO4 is donating one of its H plus, so it's obviously acting as an acid, not a base, okay? And now if you look at HCN, again, HCN is donating one of its it's donating its H plus to become CN minus itself only, right? So it's also an acid, it's donating H plus. And now if you look at HCO3 minus, that's a bit more tricky, but what we can do, because HCO3 minus is becoming H2O and CO2, so that's a bit, it's hard to see whether it's an acid or not. But HCO3 minus is actually quite a popular, should I say popular or what? But it's quite a famous base, right? It's actually um, part of like sodium bicarbonate, which is, I think, a very famous base. I don't know if any of you have ever heard of it, but like NaHCO3, okay? So as I remember at the very least, maybe I'm wrong about the formulas, but that should be it. So HCO3. So this is actually bicarbonate ion, or hydrogen carbonate, you would call it. So anyways, so what you can do is, you see HNO2, it is losing an H plus, right, and it's becoming NO2 minus. This is acting as your acid, which immediately implies that the other substance must be acting as a base. This is actually acting as a base, right? So because actually the problem is that like you get H2O and CO2. So this substance is acting as an acid, which obviously means the other substance is acting as a base. So if this is the underlying substance as well, and they're asking which reaction is the underlying substance acting as a base in. So that means C is your answer, right? And if you look at the last option, again, over here CH2ClCOOH is losing an H plus to form CH2ClCO minus. If it's losing an H plus, that means it's an acid, right? Because it's a proton H plus donor. That's what an acid is, right? Or you could say a lone pair acceptor according to the Lewis base theory, acid base theory. But in Cambridge syllabus, we have Bronsted-Lowry acid base theory only. So that's the thing. Okay, so the answer is C. By the process of elimination, like these three are acids, so these can't be the answer, and so this is your answer. Okay. And the next question is basically one molecule of hemoglobin, Hb, can bind with four molecules of oxygen according to the following equation. Hb plus 4O2 gives HBO twice, O2 four times, and this is a reversible reaction. When the equilibrium concentration of O2 is 7.6 into 10 to the power of minus 6, so this is 7.6 into 10 to the power of minus 6, okay? The equilibrium concentration of Hb and HBO2 to the power of 4 times are equal. So we can just take this as x, and this will also equal to x because they're equal, right? That's what they said. Now, what is the value of Kc for this equilibrium? Actually, I'll not take x, I'll just take y. And there's no reason for that, it's just that I just want to take y, okay? That's all. So what's the Kc expression firstly? Kc expression is HbO2 4, that's the product side, and then divided by Hb multiplied by O2 to the power of 4, right? Because your stoichiometric coefficient there is 4, right? Okay. So then what happens is that I can write this as y divided by y into 7.6 into 10 power of minus 6 to the power of 4. So if for this question, I didn't even need to really know the concentrations of HbO2 to the power of 4 and Hb because they just cancel out, right? Because they're equal. And that's the beauty of the question. So then my Kc is just 1 over 7.6 into 10 power of minus 6 to the power of 4. Okay, so I'll just do that calculation. What do I get? And I get 2.9974 into 10 power of 20, which is approximately 3.0 into 10 power of 20, which is option A. Okay, so that's my answer. Basically, I just erase some stuff for the next question. Question number 10. The double bond between the two carbon atoms in an ethene molecule consists of one sigma bond and one pi bond. So if I just draw out an ethane molecule, ethene molecule, so this is my molecule, and one of obviously when you have a double bond, you have one sigma bond and one pi bond. When you have a triple bond, you have one sigma bond and two pi bonds. Okay, in no particular order, but like that's how that's how I draw them. There is a particular order. I mean, obviously the sigma bond forms first, and then pi bonds, which are weaker bonds, they form later. So first you have one sigma bond, and then you get a double bond. Pi bond forms next, and then if you have a triple bond, then the other pi bond forms next. Okay, pi bonds are weaker bonds, and they break more easily, and they're also formed later. Okay, so anyways, which orbitals overlap to form each of these bonds? So sigma and pi. So for the pi bond, it's obviously a pp orbital, right? That sounds wrong, but yes, it's p orbital. Pp the p or two p orbitals overlap, right, to form the pi bond, and it's sideways overlap basically. Side to side overlap. I don't know, sideways. I don't know how to. Yeah, I was just say sideways overlap of the orbitals, and then which orbitals overlap to form the sigma bonds? You have you could say head to head overlapping to form the sigma bonds, right? So which orbitals overlap? Well, let's just find out. So basically, this carbon atom, the central, these two are the same symmetrical molecule, but if I just take, for example, this carbon atom, so then it has one, two, three sigma bonds. Like these two are also sigma bonds. So one, two, three sigma bonds, and no lone pairs, right? So the steric number is basically just three, because steric number is basically the number of sigma bonds and lone pairs on one of the central atoms, right? And you don't count the pi bonds in that, so it's just three, and that means by so it gives me what do you call it? I forgot the name, but it's sp2, right? sp2 hybridization and all. So you get sp2 hybridization, and because you have one s and two p orbitals, right? Hybridizing two, so then it's sp2 hybridization, and pi bonds are not involved in sp2 hybridization. By the way, it's just pi bonds are not involved in in hybridization. It's just sigma bonds, and yeah, so if it's sp2, because I have steric number is 3, that means that my it's going to be sp2 not sp3 sp3, right? Because you have a double bond. So sp2 means the answer is A. Okay, so p in pi bond and sp2 sigma bond, because hybridization is sp2, so that means sp2 is forming, right? So yeah. Now the next question. The diagram shows a reaction pathway for an endothermic reaction, which arrow represents the activation energy for the forward reaction. So activation energy is basically from the reactants to the highest peak, right? And I don't know why they've given double-headed arrows. That's really weird, but whatever they want to do. But then you're actually going to go from the reactants to the highest peak, right? And it's for the forward reaction, so in this direction basically. And well, this is not really going from the reactants to the peak. This is going from the reactants to the products, so it's wrong. This is going from 0 to the peak, so that's also wrong. And this is going from the reactants to the peak, so I think B is the right answer. And this is just going from the products to the peak, which is wrong. So the answer is B. Okay. In the industrial electrolysis of brine to manufacture chlorine, the diaphragm used is a porous screen which allows the flow of electrolytes but keeps other chemicals separate. Which substance needs to be kept separate from the chlorine by the diaphragm? So, um, so this is a problematic question because actually, yeah, even my teacher was like, she had some problems with this question because actually you could have technically two answers. It's NaOH is also right and hydrogen is also right. I think, as I remember, the mark scheme says uh, sodium hydroxide is the answer, or hydrogen. I think it was sodium hydroxide that the mark scheme said, but actually you would have both of them as the answer, and I'll just show it to you. Um, so, which substance needs to be kept separate from chlorine in the electrolysis of brine? So, so see, over here they're saying that it is important that the chlorine and sodium hydroxide produced in the process are separated um, when they come into contact, because they will react when they come into contact with each other, right? So it's important to separate them, right? But then if you look at another website, for example, I think Chem Library is a good one. Wait, let it just load. Okay, so over here, I think they mention that, yeah, see this? Since the H2 and Cl2 might recombine explosively should they come in contact in the electrolysis of brine, the cathode must be entirely surrounded by a porous diaphragm of asbestos. Okay, so that means that you could either have H2 and Cl2 as the answer, or they're saying over here, it is important that the chlorine and sodium hydroxide are separated, right? So actually, your answer could either be A or it could be C. So this is a weird question in that sense, but actually, it's not even in the AS syllabus anymore. Like electrolysis is not there, so you don't really need to worry about it too much. Okay, so yeah, I guess I just went into an unnecessary tangent, but yeah, that's basically a side note. Like both of these could be correct answers. You can check which one like the mark scheme says is right, I suppose, but it won't even come in AS anymore. So it's not supposed to be a big problem. Now, next question. The three minerals below are obtained from mines around the world. Each one behaves as a mixture of two carbonate compounds. They can be used as fire retardants because they decompose in the heat, producing CO2. This gas smothers fire. So what is the order of effectiveness as fire retardant from best to worst? So the best fire retardant would actually be the one that decomposes in the heat most easily, right? So down group two, if I just write down the elements of group two, so what happens to the ease of thermal decomposition? Well, actually, that's more of, I suppose, the logic behind it is more of a A2 concept, but basically your the size of your cation is increasing, right? So what happens is that as the size of your cation increases, the charge density of the cation actually decreases, right? Because you have the same charge, but your atomic radius has increased, which means the charge density of the cation has decreased, which means basically that it will, there is something called ion polarization, which is again an A2 concept. So it polarizes the anion less. So CO3 2 minus, it's polarized, it's basically distorted less as the charge density decreases. As the ion becomes bigger and its charge density decreases, the cation, then the CO3 2 minus anion is distorted less. So if it's distorted less, then the ease of thermal decomposition actually decreases. So your ease of thermal decomposition decreases down group 2. Okay? So that means that the best fire retardant would actually be one which has, the upper group 2 metals in it basically. So if I have BaCa and CaMg and Mg thrice Ca. Well, Mg thrice Ca has three magnesiums, so I would immediately actually think that that would be the best fire retardant. Okay, and that is huntite. So huntite is going to be my best one because Mg3Ca. Then CaMg, it will be my second best because it has Ca and Mg, like it still has both of the upper ones. Like, I mean, Be is there. We usually ignore beryllium. I don't know why, but yeah, poor beryllium. So dolomite, okay. And then we have barytoside, which is BaCa. So that's barium and calcium, and that is the worst one out of these three. Okay, so that's the logic, and your answer would turn out to be D. Great. Next question. Which observations are made when a sample of silicon chloride, SiCl4, is added to a beaker of water? No visible changes are observed. Well, let me just write down the equation first. SiCl4 plus H2O gives you SiO2 plus 4HCl. Okay, that's your equation. Let me just balance it. Okay, now it's balanced. So this is basically a solid. It's a giant covalent macromolecule, as you would know even from IGCSE. And HCl, this is formed as a gas. So steamy, white, dense fumes of HCl gas. Okay, are seen. So no visible changes are observed. That's obviously wrong because I just showed you a visible change here. And you also get a white precipitate. This is a white precipitate, obviously. And steamy fumes and a white precipitate are both observed. I just wrote that down right now. Oh, the irony. Yes. The appearance of a white precipitate is the only observation that's wrong. The appearance of steamy fumes is the only observation that is also wrong. So your answer is B. Okay. Next question. Use of the data booklet is relevant to this question. Which diagram correctly shows the atomic radii of the elements Mg, Al, Si, and P plotted against their melting points? So, what I like to do is I just write down the elements first. So, of period 3. So, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. If you would first talk about their melting points, well, magnesium and aluminium, they both have metallic bonding, right? And the strength of metallic bonding increases from sodium to magnesium to aluminium because over here, magnesium in its lattice, it exists as Mg2 plus and it's sea of electrons, right? But then aluminium, it exists as Al3 plus and it's sea of electrons, right? So obviously, firstly, Al3 plus cation has a smaller size than Mg2 plus cation, okay, because the cationic radius decreases across the period. And also, so that means that basically Al3 plus also has a greater charge, right? So it has a smaller size and a greater charge, and because of that, and basically because it has a 3 plus charge, that means that it has more electrons in its conductivity band, more electrons, like a bigger sea of electrons basically. And also the cations, because they have a smaller size and a greater charge, so then the charge density of the Al3 plus cations is actually greater, right? So if it has a greater charge density and a greater sea of electrons as well, bigger sea of electrons, and that means that the metallic bonding is stronger in aluminium, which means the melting point of aluminium is also stronger, right? Um, so that's for the cations. I'm talking about cations. I think the Al3 plus cation is more than the Mg. But if you just check the data booklet as well for that. Otherwise, even if you just use the logic of the sea of electrons, that should be enough as well. But let me just, and that isn't even in this data booklet, is it? No, it's not. So that's the problem. Well, I have my own data booklet over here with me, and I'll just use that because that's actually like, because they changed the syllabus, right? 2022 to 2024. They don't even give you the data booklet anymore, so I suppose that's why. But if you, because it's an old paper, right? So I think you're allowed to use an old data booklet. Mine is from 2019, and I'll just use that. Okay. So basically, in my data booklet, I even have the atomic and ionic radii. Maybe I just wouldn't be able to find the page, but anyways, for Mg2 plus is 0.065 and Al3 plus is 0.050 nanometers, so that's smaller obviously. So yeah, that's consistent with what I said. And yeah, so magnesium, uh, so yeah, basically what I'm trying to, so what we first figured out is that aluminium would have a higher melting point than magnesium, which is the case over here, and the case in A as well, and the case in C as well, and the case in D as well. So that's nice. Now phosphorus, because it's a covalent compound, whereas Mg and Al, they have metallic bonding, right? But phosphorus, it's covalent, like it's not, I don't want to say covalent, but it's just a molecule, right? I mean, like P is just a simple covalent structure. Sorry, why am I writing P8? It should be P4. But anyways, that has a simple, it's a covalent molecule basically. So it will have a lower melting point. So that's the case than magnesium or aluminum. So that's the case in all the options except B. So we can cross out B because over here phosphorus has a higher melting point than aluminium, right? So that's wrong. And now if we look at silicon, silicon is actually a giant. It exists as a, like the group 4 elements. They exist as giant structures, right? So that means it should have the highest melting point. Oh, actually no. This direction is atomic radius. So I was wrong about the phosphorus thing. Over here, phosphorus is having a lower melting point, and over here it also has a lower melting point and a lower melting point. So basically we can't cancel out using phosphorus. But silicon, it has the highest melting point, and over in D we don't have silicon as having the highest melting point because they've shown aluminum as the highest melting point. That's wrong, and all the other options have silicon as the highest melting point. Okay, then if you look at the atomic radii, well, the trend across a period is usually that the atomic radius decreases, right? And even if you look at the pure, like in my data booklet, which is from 2019, then it has magnesium as 0.160 nanometers, so 0.160, and aluminium it has as 0.143 nanometers. So basically, the atomic radius of aluminium, according to the data booklet, which they said they use the data booklet relevant to this question, so it should be smaller than that of magnesium, which is not the case in A, because you can see that they've shown it has higher. It is the case in B. They have shown you aluminium has a lower atomic radius, smaller atomic radius, and again in all the other options, aluminium has been shown as having a smaller atomic radius. Silicon would then have an even smaller atomic radius, and then phosphorus would have a smaller atomic radius again because you're going across the period, right? So basically, your number of electrons is increasing, but then they're all being added to the same shell, right? So the shielding effect remains the same, but then your number of protons across the period increases, right? Which means if your shielding effect is remaining the same, but your number of protons is increasing, that means your nuclear force of attraction will increase, right? So then your nucleus, so your shells sort of get pulled inside, and your atomic radius slightly decreases across a period. Okay, so that's why. And so if we have the order should basically be magnesium, aluminum, silicon, phosphorus, magnesium, phosphorus, silicon, aluminum. That's the wrong order. Magnesium, aluminum, silicon, phosphorus. That's the right order. So that means my answer is basically C. Okay. And yeah, that is the logic. Magnesium, then aluminum, then silicon, phosphorus. Okay. And the melting point order is this. Great. Next question. Chlorine is widely used in water treatment plants. Which reaction takes place when chlorine dissolves in water? That's basically just a general knowledge question. Like CO2 plus H2O. That this is a reaction like swimming pools and stuff. So that gives you Cl plus HClO. Sorry, HCl plus HClO, and this HClO can further decompose into HCl and then reactive, oxygen free radicals, which end up killing the bacteria in the water because there's like very reactive oxygen radicals, right? So that's the reaction that happens. That's why we do chlorination of water, right? To kill the antibacteria, kill the bacteria and stuff, because CO2 and H2 give you HCl and HClO, and HClO is a very unstable compound which decomposes into HClO free radicals, and oxygen free radicals. They kill the bacteria and stuff. Okay, so what reaction is this? That's just option A, right? That's your answer. Next question. Astatine At is below iodine in group 7 of the periodic table. Which statement is most likely to be correct? So I'll just write down my group 7 elements: fluorine, chlorine, bromine, iodine, and astatine. Okay. So which statement is most likely to be correct? Um, AgAt reacts with excess dilute aqueous ammonia to form a solution of soluble complex. That is not likely to be true because you know how we have AgCl, AgBr, and AgI. So AgCl, that in dilute aqueous ammonia, it gives you AgNH3 twice, and Cl AgNH3 twice Cl, right? It does that. But then AgBr, it says dilute aqueous ammonia. If it's dilute aqueous ammonia, you will not get a complex with AgBr, right? But if it's concentrated aqueous ammonia, then you will get AgNH3 twice Br. Okay, but then iodine will not give you a complex with either concentrated ammonia or dilute for either dilute ammonia or concentrated ammonia, um, because like it's not going to form the complex. Okay, so AgI, and so if AgI doesn't, like, you can see that the ability to form a complex is decreasing, right, across like down the group basically. So that means it's likely that if ClBrI 80, when we come to 80, then that probably astatine will not form a complex, right? So I can cross out this option because AgAt will not give me a complex with ammonia, especially dilute ammonia. So astatine and KCl react to form KAT and chlorine. Well, we know that reactivity actually, like if we have F2Cl2 Br2 I2 82, then the reactivity decreases down the group, right, down the halogens group. So if you have 80 plus KCl, 82 plus KCl in fact. So basically 82 is less reactive than the chlorine, right? So, and this is a chloride, but 82 like acetylene is a less reactive element than chlorine. So that means that it cannot displace chloride from KCl, right? So basically this is wrong as well. And now the next one, KAT and dilute sulfuric acid react to form white fumes of HAT. The thing actually is that you would get initially you would get K um, HSO4, for example, or you could say K2SO4 as well. That would be fine too, and you could just balance the equation. But I'm just for ease of balancing, I'm going to write it as KHSO4 plus HAT. You do get HAT initially, but then the strength of the covalent bonds decreases down. The strength of the HX bond, as you say it, like X being a halogen atom, that decreases down group 7 because you're basically, if I have, for example, HCl as compared to HI, right? So I is a much bigger atom, which means that this the distance, the bond is going to be a longer bond, which means it's going to be a weaker bond. And since it's a longer bond, it's a weaker bond. There's less overlapping as well. So it's a much weaker bond, like less overlapping of the atoms, and it's just atomic orbital overlapping, less atomic orbital overlapping, and it's a weaker bond because it's a longer bond, and as the size of the halogen atom increases. So basically if it becomes a weaker bond, we already know, like you've probably studied that, like if you have HCl bond like forming from this reaction with dilute sulfuric acid, then that is a very strong thing. It won't really break down more. But then if you have HBr gas forming, then that would break down further into like bromine, or actually no, actually I don't remember, but it does break down. I think it's Br2 liquid that forms. So or actually Br2 gas, which then we can make into liquid. I don't know exactly, but yeah. So that happens. But then if you have Hi, that's also really that's even weaker, right? So you can get from that various products like I2 and Hi, and sorry, not Hi, sorry, I2, and then it can even further um, become SO2, because dilute sulfuric acid in that case, basically H2SO4. Over here, the oxidation state of sulfur, you can check it for yourself, is +6, and over here, it's -4. So basically, this is becoming reduced, right? Basically, H2SO4 is an oxidizing agent, so it oxidizes, like in HI you have I as -1, and then in I2 you have it as 0, right? So basically with HBr and HI and all the other like below chlorine group 7 elements, your H2SO4 also does not only act as a strong acid, it also acts as an oxidizing agent, okay, to form like combustion products. Basically even sulfur it forms, which has an oxidation to 0. So this is becoming reduced basically, and it's oxidizing the iodide. Okay, so this basically what I'm trying to say is that if they're saying that KAT and dilute sulfuric acid react from white fumes of HAT, that's wrong, because HAT is a really, like the covalent bond between H and AT is really weak. So you would get, maybe you would get AT too, and you will also get other stuff because it's a really weak bond, right? So it will break down further, it will decompose further, and H2SO4 is basically able to oxidize the AT anion, so AT minus anion. Then they're saying that NaAT and concentrated sulfuric acid react to form acetylene, like just like how this happened, right? So if you have NaAT plus H2SO4, and I think again I just saw this right now that they mentioned dilute and concentrated. But anyways, if we have NaAT plus H2SO4, that will give you NaHSO4, or you could say Na2SO4 as well and balance it, plus HAT, right? So then you have HAT, and this will actually decompose further. One of the products of the decomposition, like basically oxidation of HAT, because the H2SO4 is an oxidizing agent, then you will get AT2 as well. That's right. And NaAT and concentrated sulfuric acid react to form acetylene. That's right. Okay, so I actually have to go somewhere for a while, so then I will come back and do more questions after that. All right, I'm back. So let's go to the next question. Question number 18. Moher salt is a pale green crystalline solid which is soluble in water. It contains two cations, one of which is Fe2 plus and one anion which is SO42 minus. The identity of the second cation was determined by heating Mohr's salt with aqueous sodium hydroxide. A colorless gas was evolved which readily dissolved in water, giving an alkaline solution. A green precipitate was also formed. What are the identities of the gas and the precipitate? Okay, so we have to find, so it's a pale green crystalline solid which is soluble in water. It contains two cations, one of which is a P2 plus and one anion which is a 4 2 minus. So a colorless gas was evolved which readily dissolved in water, giving an alkaline solution. If you look at the options, you have NH3 and SO2. SO2 is actually an acidic gas, right? So that means that it's wrong because they're talking about an alkaline solution. So an alkaline solution can only be formed if the gas was actually alkaline, right? A basic gas. So NH3 is a basic gas. So that must be our first thing that we have to just think about, that it's either A or B because the gas is NH3, okay? And now it contains, so basically what is the precipitate? Now if you consider FeOH twice versus Na2SO4, Na2SO4 is not going to be a precipitate, right? Because all the salts which contain Na, and in general I guess in group 1, those are soluble salts, right? So this is actually a soluble salt, so it's not going to give you a precipitate because the precipitate is solid, right? But FeOH twice, that is a solid, okay? So that's just something you should know from, like, I guess, qualitative analysis and those type of things. So the answer is basically going to be A. Okay, next question. Which mass of solid residue will be obtained from the thermal decomposition of 4.10 grams of anhydrous calcium nitrate? So let's write down the equation. CaNO3 twice, that's calcium nitrate because Ca2 plus and NO3 minus gives you CaNO3 twice. Okay, so CaNO3 twice, when it decomposes, it will give you CaO and NO2 and O2. So now if you balance it, you already have one calcium atom, then you have two nitrogen, so just make this a 2, and then 2 2s are 4, plus 1 5, then 6 7, 7 oxygen on this side, and then on this side you have 6 oxygen. So what you can do is you can just make this 1 by 2, then you have 1 plus 4 5 and 6 oxygen on this side as well, so now it's balanced. Okay, so now what mass of solid residue will be obtained? So I'm just going to say this is 4.10 grams, and so I'm just using my periodic table, okay? I you just have a periodic table with you because I don't really like the 2022 to 2024 periodic table much. Although it's a good one, but like, this is an old past paper, it's 2015, so I'm just using an old periodic table, okay? It's not that old, I mean, it's 2019. Anyways, that's not the point. So calcium is 40.1, like the MR of calcium, basically calcium nitrate I'm trying to find. So it's going to be 40.1 plus the was nitrogen is 14.0, so because you have two nitrogen atoms, so that'll be times 2, and then plus because you have 6 oxygen atoms, so 16 times 6. So what are you going to get? 40.1 plus 28 plus 16 times 6, that gives you 164.1 grams per mole. Okay, so now if you find the moles of calcium nitrate, that is going to be mass over the molar mass, so 4.10 over 164.1. So 4.10 over 164.1, that is actually 0.02498, and so on, but I'm just going to take it to these many significant figures. You just use your calculator answer basically. And now what is the solid residue? Well, this is a gas and this is also a gas, but this is the solid. Yeah, okay, sorry. So this is a gas, and so this is a solid. So because they're saying what mass of solid residue will be obtained, so we're going to just find the moles of CaO, right, first, and then we're going to find the mass of it. So this is a 1:1 molar ratio, like CaNO3 twice is to CaO, that's a 1:1 molar ratio. So if we have 0.02498 moles of this, then this is also going to be 0.02498 moles, okay, approximately. So I mean to say, that's the molar ratio we have. And now we're going to just do m equals to n times mr, right? So the mass equals to the moles times the molar mass. So now the molar mass of calcium oxide, that would be 40.1 plus 16.0. That's the MR of calcium oxide. So that's just going to be, let me just see what that would be. So 6, and then that's just going to 56.1 grams per mole, if I'm not wrong and my mental math is not too bad. But yes. So what I'm going to do is I'm just going to take 0.02498 multiplied by 56.1, and that should give me my answer. 56.1. That gives me 1.4016 grams, which is approximately 1.40 grams. Okay, and that basically is the mass of CaO that's formed, and that's the only solid product we have. So basically, that's the solid residue, right? And so that is option C. Okay, so that is our answer. And let's go to the next question now. Question number 20. Which reagent will give a different observation with compounds P and Q? So this I can see over here. I have one OH group over here, one OH group over here. So like two basically alcohol groups. So this is a primary alcohol group and this is a secondary alcohol group, and this is aldehyde group as well. So aldehyde and also alcohol groups I have, okay. And over here I have two OH groups, so that's alcohol, and I also have one ketone group, right? Because that's CO, right? Like the ketone group. So CO in the middle, but if I have CO like this, like RCOH, then that's aldehyde. If I have RCO are somewhere in like in the middle of the structure, then that is ketone, right? So that is a ketone group. So I have ketone and aldehyde. So basically, since both of them have alcohol groups, I cannot use a reagent that identifies alcohol because we need a different observation. So you have to find a reagent which would give a different like it distinguishes between aldehydes and ketones. So Br2 aqueous, well, I mean, I don't understand what the point of that is in this case, because that's more like for alkylation and stuff like that, I suppose. But then you have hot acidified KMNO4. Um, um, well, would it give you a different? I mean, because both of them have alcohol groups, right? So you would actually, in both cases, your KMNO4 would turn from purple to colorless, I guess. So that's not a really, you wouldn't get a different observation, am I right? If you have silver nitrate in ammonia solution, well, ammonical AgNO3 is called, right? So that's actually your Tolan's reagent. Like Tolan's reagent is actually silver nitrate that is in ammonia solution, right? And Tolan's reagent is a test for aldehydes. So it gives a positive result with aldehydes and a negative result with ketones, right? So that's actually your answer because it will distinguish between aldehyde and ketone. It's your silver mirror test if you want to, search it up and stuff. So it's called the silver mirror test, or like you use Tolan's reagent for it, and it gives quite a pretty silver mirror. I haven't been able to produce a perfect silver mirror, but I remember when my teacher made it in the lab, it was so beautiful. Such a beautiful silver mirror is formed, but I wasn't able to form such a pretty silver mirror, but hers were so professional and pretty. Okay, so then warm acidified K2Cr2O7, again, because you have alcohol groups, it would turn from purple to colorless, I'm sure. So I really don't think, because both of them have alcohol groups actually, so I don't think it's, you should use warm acidified K2Cr2O7, but the best reagent that will give a different observation is actually ammonical silver nitrate, because it gives a positive test for aldehyde and a negative test for ketone, okay? Because it is a test for aldehydes. Aldehydes, they give the silver mirror. So yeah. Next question. The cyclic compound M is heated with dilute hydrochloric acid. So what? Oh no, I meant my battery is running low. Let me just connect my charger. Okay, so let's look at the question. Cyclic compound M is heated with dilute hydrochloric acid. What are the products of the reaction? So this bond will be broken here and this bond will be broken here. Okay. Um, so then what happens is you get this thing. NH2, you would get NH2 first, and then this would just become OH, Okay, that's one of the products because over here you get OH added, and so that becomes COOH, and over here you get NH2. That's actually more of an A2 part, I think. I'm not actually sure. I don't know if, because I don't remember covering it in AS. I think we covered it in A2. I'm not sure. So OH, but you can sort of deduce it, I guess. I don't know. But anyways, so this gives you COOH. You get an alcohol group here and a COOH there. Okay, so that's how it happens. That's what you get. So those are the two products you get from when this is hydrolyzed. Because dilute hydrochloric acid means basically acid hydrolysis. That's what you're doing. So you're doing acid hydrolysis. And what that means is actually, because it's acid hydrolysis, so you have acidic conditions, right? So because you can see that they're giving you NH3 plus here. So the reason for that is because actually NH2 will because this amine product, like it will, like, because under acidic conditions NH2 will actually become NH3 plus, like it will gain a proton, it will accept a proton, right? Because in acidic conditions it's acting as a base, and so in acidic conditions it will just become NH3 plus, NH2 will become NH3 plus, and over here your COH and OH, they remain the same. But yeah, because that's NH2, it's a base, so it will become NH3 plus. Okay, and because it's acidic conditions, so you have to see one where you have, these two products form. Obviously you can cancel this out because it has NH2, and this is acidic conditions, as I told you. And you can also cancel this out because you don't see NH3 plus, so that I have NH3 plus over here. HOOC CH2 NH3 plus, HOOC CH2 NH3 plus, that's what I have. And HO CH2 CO, that's a different product actually that they've given me here. That's not the same product that I have. So I can cross this out as well. HOCH2 CHO. Now see, they've given me even CHO, but this is actually COOH. And then over here I have HCO. So basically they're doing it in the opposite direction. So HO CH2 COOH. So that's actually what I have over here. Or HOOC CH2 OH, right? So this is actually the correct answer. Then B. B shows these two products that I have drawn over here, right? So that's my correct answer. And the next question. Cottonseed oil contains large amounts of polyunsaturated carboxylic acids. Okay. Now, when this oil is used to make margarine, the CC double bonds in the unsaturated carboxylic acids are hydrogenated. Which reagents and conditions would be suitable to bring about this hydrogenation reaction? So that's just, basically polyunsaturated carboxylic acids and stuff. So they're just breaking the CC double bonds, right? So they're hydrogenating an alkene basically. So if you had any alkene, usually to add hydrogen to alkenes, you use these conditions, right? H2 gas, nickel catalyst, 400 degrees Celsius. So those are the conditions you use to hydrogenate alkenes. Because actually H2 gas, nickel catalyst, 400 degrees Celsius, that's a very, very strong reducing agent. I think it reduces a lot of things actually. So yeah, it's a very strong reducing agent, and for alkenes we usually do use this, I think. So H2 gas, nickel catalyst, and 400 degrees Celsius. Because actually this is a very strong bond, a double bond. So I'm not sure if the other substances are able to break it, but this is the best reducing agent in this case. H2 gas, nickel catalyst, 400 degrees Celsius. Which intermediate ion forms in the greatest amount during the addition of HBr to propene? So propene is what? Propene is basically, let me just draw it out. So propene, I like to draw skeletal formulas, okay? I just, it's my love. I like to draw skeletal formulas, but if you want, I can draw that too. CH3, and then you have C, and another C, and this is, actually it's not going to be this, right? It's going to be a double bond between them, and you have one H here, and two like that, I guess. Okay, that's the structure. So CH3, CH, CH2. So which intermediate ion forms in the greatest amount during the addition of HBr to propene? So first, what would happen is, like, you have HBr, right? So let me think. It's been a long time since I have drawn these things. But Why would you even have? Because in when you're doing alkylation, you get a carbocation, right? So carbocation means your intermediate is actually a positive ion. So if it's having a minus sign, firstly, that's going to be wrong. So we can immediately eliminate C and D. Okay, and then I'll just look at my mechanisms from AS because I just don't want to. I remember the mechanism, but I just don't want to, accidentally write any wrong thing, basically. That's my problem with this. So what I'm going to do is I'm just going to review it a bit. And yes, okay. So basically my H is here and my BR is here, right? So what happens then is that from this double bond, I can draw it under the double bond. In fact, maybe that would be better. But what happens is that like this is a region of like high electron density, right? So it causes dipoles to be induced in HBr, which I mean HBr is already quite a polar substance, but like it's stronger dipoles. Okay, so then electrons get transferred, and this substance basically breaks. So then you get it's already polar HBr, but it gets more polarized. Okay, so then what happens is, should I just make an arrow or something? Maybe I should have drawn this smaller, or I'll just erase other stuff. Okay, and make an arrow upwards. How about that? Okay, then you get, I'm just going to write it as CH3 like this, and you get C. So you get two things actually. So one of them you get CH, I guess, as I remember, and then you get CH2, and so this would be a plus over here. So either hydrogen gets attached here, or you can have it as CH3 and then uh, C H H H. Oh, actually, I think I'm doing it wrong. Am I not? So this would be plus here, but over here, I would just have this is the plus one, right? Yes, yes, that's the way to do it. And yeah, so that's the proper way of doing it. So I have CH. In fact, I can just write this as CH3. So just look at my, although organic chemistry is fun, but you have to keep practicing it, right? So that's the problem. So yeah, so that's how to draw it. And so which one would be my more, because which intermediate ion forms in the greatest amount, right? So that would be the one that's more stable. And over here, I just have, like, this is just having the effect of one alkyl group, right? And alkyl groups, they create positive inductive effect, right? They're electron releasing groups, right? So they stabilize the carbocation. So if I just have the effect of one R group here, so then that means it's less stable as compared to this one where there are two carbocations, because this is the primary carbocation, right? So this one is a secondary carbocation. Secondary carbocation will be more stable because there's this R group, CH3 on this side and CH3 on that side. So this one is actually a more stable carbocation. So actually this is the one I should be looking at, and this is option A actually, CH3, CH plus and CH3. Have I missed out a, yeah. Oh my god, what have I done wrong? Wait, I think I missed out a, yeah, because this carbon is, this already has an H, right? So I should have included that in both cases, and over here I should actually include an H. Yeah, I'm sorry for my confusion, but you know I'm just revising my AS concepts as well, like this. I suppose it's a good thing. But yeah, so this should actually, why did I remove the hydrogen that is already there? My mistake. Anything else is H2, so CH3, CH2, CH2 plus, but that's less stable as compared to the secondary carbocation, which is CH3, CH plus, and CH3, which is option A. So the correct answer is actually A. Okay? So let's go to the next question now. Now, I don't know how to pronounce that. Conine is the major constituent of the poison oil of hemlock. Okay, a pretty cool name actually. Sounds like quite a magical name, but anyways, quinine can be synthesized by reacting ammonia with the dibromo compound X. So NH3 plus CH16Br2, this is X, gives quinine plus 2HBr. So this is quinine plus 2HBr. Okay, so what is the name of compound X? Okay, so let me think about this. So if I were to remove the ammonia groups, right? So I can just sort of break these bonds basically and just add a Br and a Br on those, because then I get 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms, and then I would just add a bromine there and a bromine there, because those bromines are basically replaced by the NH2, right? Because the bromines are removed and then they, like, the thing joins together to form that NH bond thing. I hope that makes sense. But yeah, I don't know. I don't think I explained that so well, but basically the structure that I'm trying to get at is uh, this thing. So you're just keeping everything else the same, but you're just breaking that bond, like the amine thing, and you're going to add a Br here and a Br there. So those Brs get removed, and that thing joins together to give you NH, and so you get a ring, sort of, right? A better ring. So this is just an open molecule, but that's a closed ring thing, right? So yeah, basically that's what I'm trying to get at. And then what will happen? Again, I think I don't know if it is actually more of an A2 concept. I think maybe, but because amines and stuff, I don't know if we cover it much in AS. But yeah. But anyways, this is the structure, and so what is the name of it? Well, you would start from counting from here, because our bromine starts from here, so it's the more prioritized one compared to starting from this side. So 1, 2, 3, 4, 5, and 6, 7, 8. So you have 8, like a carbon chain that's 8 carbon atoms long. So it would not be pentane. It would be dibromo. Like, sorry, I don't know if it's C or D, but it's basically an octane. Okay, so I'm going to C or D, and then I'm going to see whether, like, it's 1, 2, 3, 4, 5. So I have one on carbon number 1, I have a bromine attached, and on carbon number 5, I have a bromine attached. So it's not 1,4-dibromooctane, it's actually 1,5-dibromooctane. So the correct answer is actually D. Okay? So yeah. Question number 25. 2-bromopropane reacts with a hot concentrated solution of sodium hydroxide in ethanol. So since it's ethanolic sodium hydroxide, that means that is actually NaOH in ethanol, which means it's an elimination reaction, right? Not actually a nucleophilic substitution reaction. So it's an elimination reaction because it's in ethanol, not in water, right? So if I have 2-bromopropane, well, 2-bromopropane looks like this. I just like drawing skeletal formulas, but if you write it in the normal form, that would be CH3 CHBr. You could put it in brackets if you want, or not. I think it's fine if you don't put it in brackets, hopefully. CHBr, CH3. Okay, so that's the molecule, CH3, CHBr, CH3, and so you could even write it like that. I don't know why. I just like reversing things, but yeah, a simple way of writing is CH3, CHBr, CH3. So now, anyways, what will be the major product of this reaction? But basically, the major product is just going to be propene, right? Because you're eliminating H and you're eliminating Br, right? So you get this plus HBr basically, and and also plus, and in fact no, plus NaBr and plus H2O, I think, because you have NaOH, right? So it's NaOH in ethanol, so you should get NaBr and H2O, as I remember. But the main, like, the product that you actually have to concern yourself with is actually propane, right? So even if it was to happen in the opposite direction, like this bond you're getting in double one here, that would be the same thing. So basically propene is the answer, and yeah, pretty cool. And next question now. The presence of a halogen in an organic compound may be detected by warming the organic compound with aqueous silver nitrate. So that's AgNO3 aqueous. Okay, so you're basically just trying to precipitate it, like, you know how we get AgCl, AgBr, AgI, those are all precipitates, right? Solids. So that's what they're saying. So you can detect the presence of a halogen in an organic compound by getting, a precipitate instead. So which compound will be the quickest to produce a precipitate? So that's the compound which has the weakest bond, because if you compare H Like I'm just comparing any covalent compound of the halides. Okay, so for example, if I have fluorine versus HF versus hydrogen chloride versus HBr versus HI versus H80. Okay, I ended up writing the whole of group 7. But the point is that like I think I mentioned it in some previous question as well, that as you go down the group, like for example, if this is HCl and HI, right? So the atom of HI is actually much bigger, right? So this the length of the bond has increased, so the bond has actually become weaker, and there's less overlapping as well. And because specifically the size of the halogen atom has increased, right? So that means bond strength actually decreases, right? So if bond strength decreases, that means the bond is weaker. It breaks more easily, right? It's a weaker bond. It breaks more easily. So basically, the one that will be quickest to produce a precipitate is the one which has the weakest bond present. So I have Cl, 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 FF, FFI, Br, ClF. So actually it should be compound number C. I can immediately see that because there's this bond which has iodine, right? Like if you look at, because they've only shown fluorine, chlorine, bromine, iodine, not acetylene, but like fluorine is a very, very strong bond. And then if you compare chloride, bromide, and iodide, like the ClHbr, HI, or whatever you have, uh, covalent bonds containing those like halogen atoms, then the weakest one would be like the one which has iodine, right? Out of these options, because iodine, the bond with like covalent bond of iodine is the weakest bond compared to the other halogens above it. And we don't even have acetylene mentioned there. So basically, that means that C will be the answer because it has iodine. Okay, and that's yeah. Basically, that's the explanation of the question, and I hope that makes sense. Next question: which reagent will give a different observation with compounds W and X? So what I can see here is that this OH, it's like this is the carbon atom that the OH is attached to, and then this carbon atom is attached to actually three carbon atoms directly, or like three R groups directly. R groups you can call them, or like carbon atoms basically. So I'm just going to call them carbon atoms. So it's attached to three carbon atoms directly, and that means it's a tertiary alcohol, right? So this is actually this like OH group is like it's a tertiary alcohol, and this one it's attached to this carbon atom, and this carbon atom, this OH is attached to this carbon atom. This carbon atom is attached to one um other carbon atom directly. So that means this is a primary alcohol, right? So we want a different observation for a primary alcohol and a tertiary alcohol. So which of these would give you a different observation? Well, Worm's Felling's reagent is actually a test for aldehydes, right? So that doesn't really make any sense in this context, honestly. So we just cancel that out. And NaOH aqueous, it will react with neither of them because NaOH is, why would NaOH like would OH minus substitute to OH minus? That doesn't really make any sense, does it? It's quite a pointless reaction. Maybe there is a reaction, I just don't know about it perhaps. Hot acidified K2Cr2O7, it would give you a different reaction because you know primary alcohols, they can be oxidized further into carboxylic acids, right? So this would actually get oxidized into like COOH and stuff. But then tertiary alcohols, you cannot oxidize them further because this carbon, it already has like three R groups, and so how like three carbon atoms attached to it, and then you cannot really oxidize the OH further because where would you, like, how would you form a double bond here? That would just basically become five bonds. It's quite a mess basically. It doesn't have any hydrogens to lose basically, right? Over here you can just lose a hydrogen easily and you can form a double bond, but over here you cannot lose any of these three bonds, right? They're like pretty like bonds that are very vital to the structure and all. I mean, you cannot really, you don't have any hydrogens to lose, so you cannot become like, you cannot be oxidized because oxidation is basically the gain of oxygen or the loss of hydrogen, right? So for the gain of oxygen, you need a double bond to form, but for that you need to lose one of the hydrogens. And how will you lose a hydrogen in a tertiary alcohol, right? I hope that makes sense. Hopefully, my explanation is not too convoluted or anything. And then SOCO2, again, it wouldn't give a different reaction. I think that SOCO2 will just react with both of them, perhaps. I actually don't remember if it reacts with alcohols as well as haloalkanes, or maybe one of them. See, I have to review my notes very well for AS chemistry. But either, let me just check. Actually, I'll just check and tell you. Hmm. So, yeah, actually, it does react with um, the reaction. So in my notes, the reaction I can find of SOCl2 is actually that with alcohols. So yeah, basically, for example, if I have CH3 CH2OH plus SOCl2, then which is actually called sulfuryl chloride, by the way. And this is a reaction at room temperature. Okay, so room temperature and pressure. I would assume room temperature and pressure. Basically, what happens is that you will get CH3 CH2Cl plus SO2 gas and plus HCl gas as well. So you see white dense fumes, and yeah. And basically, because like both the byproducts are gases, right? Like SO2 and HCl, and this is like not a gas, but these two are gases, so they just get escape into the atmosphere. So the haloalkane is the like only thing left. Okay, that's what I was thinking about haloalkanes, because this is actually a haloalkane, right? So from the alcohol, when you react with SOCl2, you get a haloalkane, obviously. So you don't really, because the haloalkane is the only thing left behind, so there's no need to distill or anything. You just get this product immediately, right? So that's pretty nice as well. And the good thing is that this reaction is like at room temperature, and like you can just conduct it at room temperature, right? And even the reaction of like any alcohol with PCl5, that's also at room temperature, so that's pretty nice. So yeah, yeah, good that I could review that reaction, I suppose. And yes, basically the answer is going to be B, because tertiary alcohols cannot be further oxidized, whereas primary alcohols can be further oxidized into carboxylic acids. Okay, so next question. In 1869, Ladenburg suggested a structure for benzene, C6H6, in which one hydrogen atom is attached to each carbon atom. A compound C6H4CO2 could be formed with the same carbon skeleton as the Ladenburg structure. How many structural isomers would this compound have? So if this is my compound, so let's draw this compound out with the bonds displayed, okay? So CH, and I am just going to make some triangles. Oh my god, Illuminati confirmed, am I right? But no. So this is H, and this is H, and this is C. I'm just drawing the same thing, but just in a way that's more convenient for me, basically. And so this is C, and this is C. I'm just basically making the CH bonds as well clear. And this is CH. But now what they're saying is that you are basically, so this is my structure, right? But what they are saying is that you are having the same carbon skeleton as the Ladenburg structure, but instead of C6H6, you have C6H4Cl2. So instead of two of the hydrogen atoms, you have Cl2. So for example, I could, oh, actually, I did that there. That's funny. So I have SH, but then what I can do is I can erase these and write Cl. All right. So I write Cl here and Cl here, and that's one of the structures I could have. Now, if I think of other structures I could have, let me think. So if I have the same carbon skeleton, right? Because we said that we have the same carbon skeleton, so I'll just make the same carbon, and there's actually a bond here as well. Actually, I just realized that. Yes, see over here. So that's one of the bonds, and I have the same carbon skeleton basically. So C, and then another C there and a C there. Okay, and let me just, what I can do is first I did this, like I made these two chlorines different, but what I can do is I can let me think. So another structure I could have, like you're just thinking about how many isomers you could have, right? So if I have H atoms all around, but um, instead of having a chlorine here, I keep this chlorine here, but then I have a chlorine there, okay? Or I could do it on this side as well. If I had a chlorine here and a chlorine here, that would be the same thing. So that's another isomer we could have, a structural isomer. And then let me think of some others. So if I had C, 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 and then C, C, C again. And let me just join them and join this, join this, join this. Pretty cool structure actually. I like this. And then we have these bonds. Okay. So now the other one I could have is if I hmm. See, actually, the thing is, if I had Cl over here and Cl over here, and then all of the others were H, 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 well, I mean, actually, that's the same thing as, like, basically, these two are the same structure, actually, aren't they? Because over here, like, if I consider this triangle, then I have one Cl here, and it's like the adjacent carbon atom to it has a Cl, right? And on this one as well, I have one Cl here, and the adjacent carbon atom to has one Cl. So actually, these are the same thing. So that's not an isomer, basically. But let me think of another one. So C, C, C. C, C. Okay, this is getting really messy. I'll make one below. How about that? C, 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 C. Okay, now that's not enough space. I need to find some space to do this as well. That's a problem. I'll just do it here, in fact. Perhaps that's better. C, 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 and C, C, C. Okay. I hope that's not too messy, but it's still okay. It is messy. That's pretty sad. My bad handwriting is coming back to bite me. So yeah, that is the structure. And okay, so this is really too messy. Even though my standards of messiness are really really high, like I'm really good at being messy, but this is too messy for me. Okay, so now what other structure could I have? Well, if I had a Cl here and a Cl here, that would again be the same as this structure. Okay, so that's not a different like a different isomer. But if I had a Cl here and a Cl over here, okay, that would be different. Now that would be different. That's a different structure because basically I have one carbon atom here and it's not on the opposite, like it's not on the carbon atom directly below it, but on a carbon atom adjacent to it. Okay, and like on the same vein, if I had one Cl here and a Cl here, that would actually be the same thing as I just drew, because you have a carbon atom here and then on the carbon adjacent to it you have a Cl, right? So those two are actually the same thing, this one and also like these two structures are basically the same. So unique structures, I only have these three unique structures: 1, 2, and 3. So one where both of them are below, and one where one of them is above, and one of them is in on a different like adjacent type of carbon atom, but like below, but not directly below. And then the other one is like the third one is where I have them directly below each other, like one is above and one is below. Okay, so the three isomers I can think of. So I would say that the answer is just three. Then how many structural isomers could this compound have? Three. So basically, for these type of questions, you just have to really think how many structural isomers you have, and you have to go about it systematically, perhaps more systematically than I do it, because I'm a very messy person, so just do it neatly, okay? So yeah. Question number 29. Citrus, the citrus flavor of lemons is due to the compound limonene, this is a pretty name, present in both the peel and the juice. What is the mole ratio of carbon dioxide to water produced when limonene is completely burned in oxygen? So if you just count a number of carbon atoms you have in limonene, that's the moles of carbon dioxide that you will have. And so let me just first count the number, because limonene is basically just carbon and hydrogen, right? You don't have any other element in the structure. So let me just count the number of carbon atoms first. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C10. And then how many H's do I have? Hydrogens? Let's see. So I have 1, 2, 3 hydrogens here, because carbon forms 4 bonds usually, right? In organic chemistry, especially. So let's just see 1, 2, 3. And then over here you already have 4 bonds. There's no space for hydrogen, so 3 hydrogens there. And then over here you have 1, 2, 3 bonds here. So that means the fourth bond must be hydrogen. So that's 4. I'll just keep a tally here, okay? 1, 2, 3, 4. And then over here you have two hydrogen bonds. So not hydrogen bond, perhaps I shouldn't say that because that's an intermolecular force, but two bonds with hydrogen. Anyways, you get the point, right? Like one hydrogen atom here and one hydrogen atom here. Let's not be so pedantic. That's a word my brother taught me recently. So yeah, that's 1, 2, 3, 4, 5, 6, and 7 because there's one bond there, and then 8, 9, and then 10, 11, and then over here you have four bonds already, so there's no space for hydrogen, and then 12, 13, 14, and then over here you have 15 and 16. 15 and 16. So if you have 16 hydrogen atoms, okay, so that means C10H16, okay. So now you have CO2 and H2O formed, and it's completely burned in oxygen, right? So plus O2 gives you CO2 and H2O. I'm not bothering with balancing everything, but basically you get okay, that's a problem. Did I count the number of moles of carbon dioxide right? C10H16. I think I did. But oh, okay, they're just talking about the mole ratio. So this is 10, and then this is the moles of water are basically going to be half the moles of hydrogen, right? Like for example, if I have 16 hydrogen atoms, then because H2O contains, like in its structure, it contains two hydrogen atoms, right? So this is going to be 16 by 2. Okay, 16 by 2 H2 because that gives me 16 of H atoms. 16 by 2 actually means 8 H2O. Okay, so I actually have 8 moles of H2O. Okay, 8 moles of H2O. I hope that makes sense. Um, and because then I'll get 16 H atoms as I have in the structure, as you can see. So that means that the what is the mole ratio? So they're talking about ratio. So I'll take it as of carbon dioxide to water, right? So CO2 to water is going to be 10 is to 8. Okay, so 10 is to 8. I can simplify that further. I think because I don't see 10 in the options, right, for carbon dioxide, so probably they've just divided this by 2 to simplify the ratio. So if you divide both of them by 2, you get 5 is to 4. Is that an option? 5 is to 4. Yeah, that's an option. So that's option number B. So that doesn't make sense. Option number B, option letter B, whatever. But you get the point. So it's option B. So that's B. Great, great. And now let's go to the next question. Um, all right. What is the organic product when ethanamide CH3CONH2 is boiled with excess aqueous sodium hydroxide? So excess aqueous sodium hydroxide, I suppose that's a base hydrolysis, right? You're basically hydrolyzing it using a base. My God, my handwriting is just a different level of beautiful today, isn't it? That's, sarcasm basically. But yes, I really should improve my handwriting. But anyways, this is CH3. Let me just write it like this: CH3 and CO and H2, right? So what I can do is I can just hydrolyze this. And what is the organic product you get? So this is going to just give you, I guess, NH3 on this side. But over here, you're going to get CH3, COOH firstly, but then because it's a basic environment and this is an acid, so it's going to basically react with NaOH, right? That's that's the basic environment. You have NaOH aqueous. So then basically what do you get? You get CH3 COO minus ion and then Na plus, right? From this, and because they're going to react with each other to give you CH3 CO minus Na plus H2O, right? So you get H here and for O from there to give you H2O, and these two react to give you CH3 CO minus Na plus. So the answer should be D, basically. I hope that makes sense. And you also get NH3 obviously from this. I guess that's how hydrolysis of amides works, to my knowledge. That's what I remember. Okay. If I do anything wrong, you can obviously tell me in the comments. That would be great. And now we come to this section B, which is no longer in the syllabus, but it's still a pretty cool question, like section if you want to just practice your chemistry and stuff. So use the data booklet is relevant to this question. Again, I'm not going to use the new data booklet. I'm just using my old one. Okay, you can keep a data booklet yourself too. That would be nice. And so the isotope 99 Tc. So Tc, where is that in my periodic table? That is technetium, and that has a atomic like a proton number of 43. Okay, so technetium, it has a proton number of 43. It's in D block. So it's radioactive and has been found in lobsters and seaweed adjacent to nuclear fuel reprocessing plants. That is really interesting, actually. Anyways, uh, what statements are correct about an atom of 99 technetium? So as I've already told you, it has 43 protons, so this statement is correct. It has 99 nucleons, that's also correct. We can see that over here. This is the number of nucleons. It has 13 more neutrons than protons. So if we find out how many neutrons it has, so n equals to 99 minus 43, right? So 99 minus 43 would actually be 56. Okay, and now if you find the difference between the number of neutrons and the number of protons, right? So that's 56 minus 43. So that 56 minus 43 is actually going to be 13. So if it says that it has 13 more neutrons than protons, this statement is actually true as well. We just saw it right now, proved it. So then that means that our answer is A, right? 1, 2, and 3 are correct. B means 1 and 2 are correct, C means 2 and 3 are correct, and D means 1 is only correct. You don't need to do this section actually because it's no longer in the exam, but I just like doing it for practice and stuff. So yeah. Urea, and also to see, different types of questions. So urea is a product of animal metabolism. Okay, cool. It can also be used as a fertilizer. So the diagram shows angle X in this molecule. Which statements about the structure of urea are correct? The molecule has two pi bonds. Well, I can only see one actually. So that means this statement is wrong, which immediately means that the answer is D, because according to how the question, like how the structure of this section is framed, that actually immediately means the answer is D. But if let's just look at option number 3 and 1 as well. The molecule has only 3 lone pairs of electrons, but it has one lone pair over here, then another lone pair on this nitrogen atom. Okay, because nitrogen has 5 electrons in its valence shell, right? But then 3 of them are used in bonding over here, 1, 2, 3 bonds that nitrogen forms, and then you have one lone pair basically. And then oxygen, it has 6 electrons in its valence shell, right? And it's forming 2 bonds, which means that it has 2 lone pairs. So actually there are 4 lone pairs of electrons, 1, 2, 3, 4. So the molecule has only 3 pairs of lone pairs of electrons, wrong. And if you look at option D, one, sorry, question of option 1, angle X is approximately 120 degrees. Well, if we find angle X, so basically the steric number, or the number of, like, the total number of lone pairs plus sigma bonds in this for carbon over here, because we're considering angle X, will take carbon as our atom that we're looking at. So there's one sigma bond, this is a pi bond, and pi bonds are not considered when we're talking about steric number. So there's one sigma bond over here, and another sigma bond over here, another sigma bond over here. So 3 sigma bonds, and there are no lone pairs, so we can just take it as 0. That gives you a steric number of 3, right? So that means that it has an sp2 hybridization, basically 1s plus 2p. So that gives you sp2. And so that your hybridization is sp2, and the bond angle for sp2 is 120 degrees, right? So angle X is approximately 120 degrees. That is true according to what we know about Vesper theory and like valence electron pair repulsion theory, and lone pair repulsion and all that stuff, lone pair, bond pair, whatever, they know all that stuff. So basically that using that knowledge, we can say that angle X is approximately 120 degrees. But the other two statements are wrong, obviously. Okay, so that's question number 32. Question number 33. Aluminium is extracted from aluminium oxide, which is Al2O3, or also known as bauxite. Because well, bauxite is actually an ore, but the main thing in it is aluminium oxide. So by electrolysis, which statements are correct? Aluminium oxide has an extremely high melting point. That's right. That's why we're trying to lower it by adding cryolite, because actually its boiling point is reduced using cryolite rather than water. Bauxite is added to the aluminum oxide to lower its melting point. That's quite a weird statement, because bauxite, the main constituent of bauxite is Al2O3, and then you're adding Al2O3 to Al2O3 to lower its melting point. That's quite a weird statement. So no, that's really wrong, basically. Oxygen produced the graphite cathode reacts with the graphite to produce CO2. Actually, it's the oxygen produced the graphite anode reacts with the graphite to produce CO2, because oxygen is produced at the anode, actually. Anyways, again, electrolysis is not in AS anymore, so you don't really need to worry about this. But I Just wanted to do the question because I'm just solving the whole paper, right? So yeah. And I like MCQs in general. So yeah, the answer is basically just D. Okay. Next question. But you don't really need to worry about it for Cambridge AS basically. So why does raising the pressure of a fixed mass of gaseous reactants at a constant temperature cause an increase in the rate of reaction? Okay, so you're raising the pressure. So basically, we know from Boyle's law that pressure is inversely proportional to volume, or perhaps a better way of writing that would be pressure is like this, directly proportional to 1 over volume. The pressure is inversely proportional to volume, or volume is inversely proportional to pressure. That's Boyle's law at constant temperature. At constant temperature, obviously. Okay, and so why does this cause an increase in the rate of reaction? More collisions occur per second when the pressure is increased. That's right, because if your pressure is increased, then your volume is decreased, right? So the particles are much closer to each other, which means they collide more frequently because they're closer to each other. Okay, so there's more chance of them meeting, basically. That's right. Now, more molecules have great energy greater than the activation energy at the higher pressure. That's wrong because your temperature is constant, and also you don't have a catalyst or anything that they're mentioning. So pressure has nothing to do with molecules having greater energy than activation energy. That's wrong, which immediately means our answer is D basically. But again, if you look at the third statement, raising the pressure lowers the activation energy. That's directly related to statement two. No, obviously not. How can raising the pressure lower your activation energy? Only a catalyst can do that, right? And having energy greater than activation energy, that can only be done either by temperature increasing or by the addition of catalyst, right? So now, because temperature will lower your peak in a Boltzmann curve, so then there's more area on the graph in that sense. See, I'm not really good at drawing this problem, but if I was, I would draw more neatly. See, I'm not, because these lines are not actually supposed to cross. But anyways, maybe if there's another Boltzmann question one day, I'll explain it better. But and then your uh, activation energy shifts, like the peak activation energy shifts to your left hand side, like using a catalyst. The catalyst shifts to the left. I think the first question was something about that. So yeah, basically the answer is D. And then I just ramble on a lot, don't I? Anyways, question number 35. Which statements about the industrial manufacture of sulfuric acid are correct? So sulfuric acid is H2SO4. Sulfur is burned to form sulfur dioxide. That's right. That's the first step. S plus O2 gives you SO2, right? And then the stage that forms sulfur trioxide involves a V2O5 catalyst. That's also right. So then after this, you have the stage where SO2 plus O2, or actually I should say 1 by 2 O2, and this is reversible reaction gives you SO3. So you do use a V2O5 catalyst for that, and around what was the temperature? So you use a 2 atmospheres pressure, and I don't actually remember the exact temperature. Was it 450 degrees Celsius? I think so. Um, so yeah, you can correct me in the comments if I'm wrong, but as I remember, the temperature is 450 degrees Celsius for that process. I'm just trying to see if I can find that out. Um, Let me see if I can. See, I'm just looking through whether I have that in any immediate notes I can access. Oh yes, okay, fine, I found it. So yeah, it is 450 degrees Celsius. That's nice. It's 450 degrees Celsius and around 2 atmospheres pressure. Okay, and use a V2O5 catalyst, obviously. And the stage that forms sulfur trioxide is non-reversible, but no, actually I have shown a reversible sign here because it is reversible, so that's wrong. So you have 1 and 2 as the correct options with correct answers, which means your option B is the right option. Okay, so B is your answer here. And let's look at the next question now. Question number 36. So what is that? X is a group 2 metal. It forms a sulfate. I'm just going to erase some things. So it forms a sulfate. So group 2 metals are beryllium, magnesium, calcium, strontium, barium, and radium. Okay. So it forms a sulfate, which is more soluble than barium sulfate. It forms a hydroxide, which is more soluble than calcium hydroxide. Okay, down group 2 basically, and that's more of an A2 concept, but your solubility of the um, hydroxides, basically, I don't know how to write it, but your basically, I'll just write it here. So, um, MOH twice. Okay, I'm just going to denote the a cation of that as M2 plus. So then I get MOH twice. A group 2 cation, a group 2 hydroxide MOH twice. The solubility increases down group 2. But if you have a sulfate, then the solubility uh, decreases down group 2. Okay, and that's more of an A2 concept, basically to do with like enthalpy changes of solution and lattice enthalpies, and also enthalpy changes of hydration. So it's basically related to that, and um, the size of the cation, basically. So yeah, it's related to that, basically, and the logic behind this, basically. And so if it's more soluble than barium sulfate, the sulfate, that means it's above barium sulfate, right? So it's either strontium, calcium, magnesium, or beryllium. So till now I haven't really eliminated any of these options. It forms a sulfate which is more soluble than barium sulfate, so that it could either be strontium, magnesium, or beryllium. Okay, but then it forms a hydroxide which is more soluble than calcium hydroxide. So calcium is here, which means it can only be strontium, right? Because it's above barium, but then below calcium, which means the only possibility of it is strontium. Okay, so basically strontium is my correct answer. Magnesium and beryllium are out. So the correct answer is going to be D. Next question. Um, Diagram shows the structure of an alkene molecule. What statements about this molecule are correct? All the carbon atoms are in the same plane. Well, for this is 120 degrees, right? So this is sp2 hybridization, because it has three sigma bonds and no lone pair. So that's sp2 hybridization, and those three do lie in the same plane because it's 120 degrees. So it is actually called, in fact, trigonal planar, right? So planar means it does lie in the same plane, right? But then the thing is, that's not the only hybridization you have in the molecule. For example, you have over here four sigma bonds and zero lone pairs, so that's sp3 hybridization, right? And that is 109.5 degrees, if I'm not wrong, and that is a tetrahedral structure. Right? So that's actually not in the same plane. It's more of a 3D type of structure, and that means that they do not lie in the same plane. So because it's 109.5 degrees, right? It's quite a tree type of structure. So since we have sp3 hybridization, in the molecule, and like this is also sp3, this is also sp3, like this carbon atom also has sp3, and sp3 hybridization near like 109.5 degree bond angles and all. So that means that all the carbon atoms lie in the same plane. That's not possible. That is a wrong statement, according to, like, if we investigate the hybridization and bond angles and all, right? If you look at the angles, they cannot lie in the same plane. 109.5 degrees, how can that be in the same plane? And if you look at it has geometrical isomers. Well, geometrical isomers means basically cis-trans isomers, right? Can we have cis-trans isomers? Let's check. So, well, we have a double bond. That's one thing. And then these double bonds are located on different, like, basically each of the carbon atoms involved with a double bond, which is basically this one and this one, they have different groups attached. Like, it's not like I have CH, Mn, R, whatever this thing is, I'm just denoting it as R, and CH3, right? So then you wouldn't have cis trans, right? Because these two carbon atoms, they have like this carbon atom has the same groups attached, like on like the same two groups attached, right? But over here you have two different groups attached, like one CH3 and one H, two different groups attached to this carbon atom, and then on this carbon atom as well, you have two different groups attached, CH3, this whole thing, and also this CH3, right? So that means you can have cis trans here, right? I hope that makes sense. Basically, you can have cis trans here, which if you can have cis trans, that means you can have geometrical isomers, because geometrical isomers are cis trans isomers. That's right. Now, the next thing is, it is optically active. Well, to be optically active, you're supposed to have a chiral carbon atom, right? And do I have a chiral carbon atom here? That means a carbon atom which has four different groups attached to it. Let's check. So these two cannot be chiral carbon atoms, because chiral carbon atoms should have four different groups attached. And if you have a double bond, that immediately means you don't really have four different groups attached, right? You just have, because you have two bonds to one of the same groups, right? So that's just immediately wrong. And this one again, it has a double bond, so we can immediately cross out this carbon atom. But this carbon atom, it has one of the groups this, and this is the other group, this is the other group, and this is the other group, right? All of these four groups that it's attached to, this H and this thing and this thing and this thing, these are all different groups, right? So I would say that this is a chiral carbon atom, wouldn't you? So basically that is my chiral carbon atom here, this one that I'm going to circle now. And this is obviously not a chiral carbon atom, this one, because it has two H groups attached. Okay, so that's not chiral. But I do have one chiral carbon atom, which means that this molecule is optically active because it has at least one optical isomer, right? It has one optical isomer, which means it is optically active because, yeah, it has a chiral carbon. So that means I have 2 and 3 are correct, which means my option is C according to the scheme that they've given. 2 and 3 are correct, okay? So C is going to be my correct answer. And now if I look at question number 38, sorry, then that is an organic compound X will react with calcium metal to produce a salt with the empirical formula CaC4H4O4. What could be the identity of X? Okay, so ethanoic acid. So if I draw out ethanoic acid, that's basically CH3 and then COOH. So now if it reacts with calcium metal, what will happen is that calcium is a basic metal, right? And this is an acid. So then I would get CH3COO. Actually, I'll get CH3COO. I'll just write it like in this form because I think it will be easier if I write it as CH3COOH. Okay, in this case. So that plus Ca, that would actually give me CH3COO. Sorry, CH3 because Ca2 plus. So basically, I would get an ionic compound, right? So CH3COO twice Ca because CH3COO has a negative charge, so CH3CO minus, and then Ca2 plus, right? So if I cross multiply, I get CH3COO twice and Ca. Okay, that's the ionic compound I get. Plus hydrogen, obviously. So you can make it 1 by 2H2. Okay, plus 1 by 2H2. So it's a similar reaction to what you get with sodium. When sodium metal reacts with carboxylic acid. Okay, so is that the same as CaCH4 is this thing? So I have two carbon atoms, so that's C2, and actually no, I don't have C2 because I have two carbon atoms here, and then so that makes it 2 times 2 because this is 2, so I give me C4, and then I have 3 hydrogen atoms times 2, that becomes H6, and then I have 2 oxygen atoms here times 2, that becomes 2 times 2 4, so O4, and then Ca. So C4 at 6O4 Ca, that's actually not the same compound, is it? So that means that it cannot be ethanoic acid. So that option is out. Now let's look at butane dioic acid. I'm just going to erase this and check for butane dioic acid. Sorry if it's very messy work. Tell me if you would like me to, you know, make some other arrangement to do work neater. But butane dioic acid. So butane dioic acid basically means I have the structure of butane, and then dioic acid, so I have OOH over here, and then OOH over here. Okay. So what I would get then if I react calcium metal with it is, because this will have a 2 minus charge, right? Because if I lose this, I get O minus, and if I lose that, I get O minus. So basically, I don't need to do the, the same thing I did with CH3COO twice here, where I added twice there because it already has a 2 minus charge. It's the compound if I lose the H atoms. So I will basically get CaO, and this thing OOCA, and obviously I'll get H2 as well. Okay, so if I react with calcium metal, and so is that the same as this thing CaC4H4 over the C? So I have Ca2, and then I have 1 2 3 4 O4. Am I doing that right, or should I only change one of the things? Like, should I only add one calcium? Let's do that. Let's just add one calcium. Maybe we can check if that is the right answer. I don't know if I'm doing this right actually. So 1, 2, 3, 4 carbon atoms. So C4. And then how many hydrogens do I have? Okay, let me just erase that a little bit. Okay, so I have Ca, C4, and then how many hydrogen atoms do I have? 1, 2, 3, 4, 5. That's a problem. I don't know if I've done this right. I don't know. I'm not really sure whether I've done this question right or not. We react with calcium metal to produce a salt with the empirical formula CaC4H4O4. So butane dioic acid, so it's basically CH3. Let me think about this. Butane dioic acid. 1, 2, 3, 4, and 5. Why am I getting 5? Obviously I'm getting 5 because I put an OH there. Is there a way not to get an OH? Should I put an O minus there or something? This is a good question. Or maybe if I have CH3COOH, can I just make it Ca? Oh, twice Ca, right? Can I, perhaps maybe I'm supposed to do that? An organic compound X will react with, let me take some time to do that and I'll come back to this sheet. Okay, so I took some time to try to figure it out myself, and I think I get the logic now behind the question. So basically, I already explained the ethanoic acid part, but then for butane dioic acid, basically you have this structure, right? So this structure, like if I just write it down, like 1, 2, 3, 4, so C4 and 2, 3, 4, so H, sorry, if I even if so yeah, okay, H4. So if remove the hydrogens because they're going to form hydrogen, like if you react a metal with an acid, then you're going to get hydrogen gas, right? So I've removed the hydrogens from both sides because those are both acids, so you lose the hydrogens, so you get H4, and then 1, 2, 3, 4, all 4, and then because you have a charge minus charge here and a minus charge here, in total that makes 2 minus, right? So this is actually, your butane dioate ion, I guess you would call it, and it has a 2 minus charge. And now, because you have Ca2 plus, right? So actually, the ionic compound you would form is actually like, because you have 1:1 molar ratio between them, like if it's 2 and 2. So if you cross multiply and ionic compounds, their empirical formula is the same as, like their molecular formula is the same as their empirical formula, right? So you would actually get C4H4O4 and Ca. So that would 2 minus and then Ca2 plus. So that's actually the ionic compound you get. So basically that's the logic behind the question. So if you check it out, then CaC4H4O4, that is actually your empirical formula for the compound. So basically that was the, yeah, logic basically. Because I'm actually used to, like, sodium and stuff, but you should also be used to like things like calcium, I suppose, where charge is 2 plus, not Na plus simply. So yeah, basically this was wrong as we established before, but this is right. And now if you check out 2-methyl propane dioic acid, then propane, firstly it has 3 carbon atoms, and then dioic acid means it has CO, OH, and again on the other side it has CO, OH, and then over here it has a methyl group, right? So again, you're going to get, when you react it with a calcium metal, then you're going to firstly, because metals plus an acid, they give you a hydrogen gas, so we can make it like O minus over here and O minus over here. So this is the ion you get, and it has a 2 minus charge. So then if you check out, if I can write the ion down like 1, 2, 3, 4 carbon atoms, so that's C4, and then 3 hydrogen atoms. Am I forgetting? Yeah, okay, so there should be 1 hydrogen atom here as well because carbon forms 4 bonds. My mistake. Yeah, just be careful in organic chemistry. I guess I'm just not a very careful person. And then 1, 2, 3, 4, so O4, and then this has a charge of 2 minus, right? And so it's reacting with Ca2 plus, and then that gives you C4H4O4 and CaC4H4, right? So Ca2 plus C4H4O4 2 minus. That's the ionic compound you get. So that means this is also correct because it's the same, CaC4H4O4. But then with ethane dioic acid, you got a different thing, right? Like it was CH3COO minus, that's the ethanoate ion, and then for that you need 2, because CH3CO minus only has a 1 minus charge, right? So you need 2 of those, and so it becomes CH3COO twice Ca. So that's actually a different that you would get, I think, what's it, C4 H6O4Ca, right? And that's not the same thing. So that's the one that's wrong, and 2 and 3 are right, which gives you the answer as C. Which compounds will react with HBr to give the compound R? So let's see then. So you're reacting it with HBr, right? And if I look at option 1, so if I react this with HBr, what would I get? Well, this will get substituted to give you Br, right? And so that works. This would give you compound R basically. That's right. And if I look at the second one, well, if I reacted with HBr, this one, then I could get I could either get my hydrogen substituted there and my bromine substituted here, which is basically the compound that they're talking about, which is right. So I would say that this is also right. Or alternatively, bromine, my hydrogen could be added on this carbon atom, and my bromine could be added here, right? So on this double bond. So that could also be formed, but basically they're asking which compounds will react with HBr to give the compound R. That's right, you could get this. And if I look at this one, well, this one can, firstly, it can give me, like if you break the double, you're adding bromine, HBr across the double bond. So yes, you could get that because you can add your bromine here and your hydrogen there, right? So you would get this compound that they're talking about, or alternatively, like the same compound, right? Because you have one like CH3 over here and one Br over there. Or alternatively, you could also get this compound, right, where your bromine is added here and your hydrogen is added over here, right? So that's another compound you could get from that. But actually, all three of them could give the compound that they're talking about. So I will say that the answer is actually A for this. Like all three compounds can actually give you the compound R. It's possible, basically. So it works. And now we finally have the last question. I think I rambled on a lot today and I messed up a few times, but we're all just here to learn, so that's fine. So 5-hydroxypentanoic acid is readily converted into cyclic compound L. So it's converted into cyclic compound L. If you hydrolyze it, then yeah. So which statements about this reaction are correct? So acidified sodium dichromate 6 is used as a reagent. No, because that is actually an oxidizing agent, and you're not really oxidizing. This is basically just esterification. You're combining, like you're reacting an alcohol with a carboxylic acid. I mean, basically you're just it's a well, one side has an alcohol and one side is a carboxylic acid, and then they combine to give you you know um and cyclic ester, I suppose. I don't know what to call it exactly. I guess it's called the cyclic ester, I would assume. I don't know. So a water, but more importantly, this is the structure. So a water molecule is produced in the reaction. Yes, because like when you have CH3COOH and you have CH3 or CH3CH2OH combining, then how does the ester form? Well, you lose OH from the carboxylic acid and you lose H from the alcohol, and then you get the ester part, and you also get H2O lost, right? So a water molecule is produced in the reaction. That is right. The reaction is catalyzed by concentrated H2SO4. Yes, you do use a small amount of H2SO4 concentrated to catalyze the reaction of esterification. So the last two options are right, and so your answer is, well, what's the answer actually? 2 and 3 correct means that the answer is C. Okay, so that is the answer, and I don't know if this has been my longest video till now, but I think it has been. But it was fun. I enjoyed the session, and I, you know, took some time to solve the paper, but I hope it was useful. And thank you for listening. All right. Have a nice day as well. So bye.